this lesson is going to be about chain rule. And once we learn how to do chain rule, we have really opened ourselves up to all kinds of new derivatives we're going to be able to take and not have to do quite as much work on some of them. Let me give you an example. Let's say we had y equals 3x minus 5 squared. Right now, the only way I could take the derivative of that is to expand it and make it square the first term, 9x squared, square the last term, plus 25. Multiply these together and double it, so be minus 30x, or you could FOIL it out. And then I could take the derivative and get 18x minus 30. Okay, that's the only way we can do that. Where this could get really ugly would be if that was like to the 21st power, and then we had to take a derivative. We wouldn't want to expand that out, so we were trying to look for a shortcut to maybe do that. So let's look at this same problem, just a little different. What if we had, same thing, 3x minus 5 to the second? If we kind of applied the properties we already have with the power rule, it'd be really nice if all we had to do was take this 2, put it down in the front, and then just drop our exponent down like we normally do. Okay? Well, as it turns out, that actually is part of the answer. I'm going to go back and remember the answer we got a minute ago was 18x minus 30. Okay, so that's when we did it the long way. So let's look at this and see if we could figure out something we could do with that. Well, if we notice, 18 and 30 are both divisible by 6. So if I take a 6 out, I could get 3x minus 5. Well, that's nice because that is what we have here. Then what I could do is, let's see if I can't rearrange this, because I'd really like for it to look like this. 2 times 3x minus 5. Well, if I do that, I could change this to be 2 times 3x minus 5. But then I could multiply by 3 at the end. That way, 2 times 3 would give me my 6 in the front, and I'd have my 3x minus 5. Okay? So it looks like that we can use this same idea of pulling our power down to the front and dropping the exponent down. But then we get this extra times 3 that we have here. So what can we do with that? Where's that coming from is what we're trying to figure out. Let's look at another one and see if we can figure out where we're getting that extra value from. So let's say we had 5x cubed plus 2 squared. Now our shortcut says it would be really nice if we could just pull that power to the front, drop the exponent down, and that would be the answer. So let's expand it. So we're going to do it the long way. So we'll expand again. We'll square the first term. It's going to give me 25 x to the 6. Square the last term, plus 4. Multiply these together and double it. So that's going to give me a plus 20x. So now that we've got that, let's go ahead and take the derivative from there. Oh, that's 20x cubed, not just 20x, sorry. So let's take the derivative from there. Well, y prime would be 25 times 6 is 150, x to the 5th plus 60 x squared. And now let's manipulate this and see what we can do with it. So let's take 150 and 60 are both divisible by 30. And then we've got x to the 5th and x squared. So I could factor out an x squared. Well, that turns out nice because that's going to give me my 5x cubed plus 2, which was what we had up here. Now let's rewrite this, because we would like for this to have a 2 in the front of it, so it follows the same format. So put a 2, 5x cubed plus 2 times, well then this would have to be 15x squared. So again, if I do 15x squared times 2, I get that 30x squared. So this is the correct answer, except for we've got this extra 15x squared we've got to figure out. Well, now, if you'll go back and notice, hopefully you kind of see where that's coming from. If I take that derivative of 5x cubed, I get 15x squared. If I go back here and look at, this was correct, except we ended up with an extra times 3. So where is that coming from? Well, it comes from 3x minus 5. If I take its derivative, I get 3. That's the whole idea behind chain rule. Okay? It says that if you have, let me just kind of put this in terms that'll make sense to us. If you've got f of something, so it's not just an x on the inside, okay? Then what you're going to do to take the derivative is, you take f prime of the something times the derivative of the something. So let me go back and show you that with the ones that we were working on. Okay. So here's how I kind of think of these. So we look at this, we've got, all right, 3x minus 5 squared. So you've got something squared. What's the derivative of something squared? It's 2 something to the first times the derivative of the something. The derivative of 3x minus 5 would be 3. Then I can multiply my 2 times 3 and get my 6, and then 3x minus 5. Our second example, same kind of thing. Think of this as something squared, so its derivative would be 2 something to the first. And notice I'm filling in those same things in the parentheses, which is really, really important. Whatever's in the parentheses here will be in the parentheses here. Then times the derivative of the something, the derivative of the inside, which is 15x squared. So that's the whole idea behind the chain rule, is that we now can take things that are being raised to powers that aren't just x and take their derivative, or the derivative of, like, sine of something that's not just an x. So let's look at same thing in function notation. And they say if you've got f of g of x, or in this case the g is the something, then what you're going to have to take the derivative is you take f prime and you keep the something times the derivative of what's on the inside. That's something times g prime of x. Now, I want to just kind of wrap up with a bunch of examples of different kinds of things we're going to do with this. Understand we are going to practice the derivative using chain rule and all the other rules. We're going to start combining those. So let's start with something fairly easy. X squared plus 3 to the 5th. Okay, what's y prime? So we've got something to the 5th. So the derivative of something to the 5th is 5 something to the 4th. So that's 7x squared plus 3 times the derivative of the something. So you go back to the inside, and the derivative of 7x squared plus 3 would be 14x. Now I try to combine my terms, and I can take the 5 and the 14x, since this is all multiplication, and do commutative property and multiply in any order. 5 times 14 would be 70. So I have 70x, 7x squared plus 3 to the 4th. And that's your answer. All right, let's try one with the trig function. How about the derivative of sine of 4x? The derivative of sine of something is cosine of something. So the derivative of sine of 4x is cosine 4x. Again, remember, whatever's in parentheses at the beginning is in parentheses at the end, then times the derivative of the inside, the something, which would be 4. Now we can move the 4 to the front. Our answer would be 4 cosine 4x. Let's try one a little more difficult. Y equals cosecant x squared minus 1. The derivative of cosecant of something is negative cosecant of something, cotangent of something, times the derivative of the something. So if I take the derivative, and we always go back to here, back to the original problem, and the derivative of x squared minus 1 would be 2x. Now again, just moving stuff around and rearranging. I've got a negative in the front here, a 2x at the end, so I can put those to the beginning and make it negative 2x, and then cosecant of x squared minus 1, cotangent x squared minus 1. Let's use one that has some of our properties that we've talked about before, some of the other ways that we can take derivatives. Let's say we have y equals 4 over sine cubed x. First thing I would do is probably rewrite this rather than do it as a Hody high, because you've got a constant on the top. So how about we make this 4 sine of x to the negative 3. So then the derivative would be 4, the derivative of something to the negative 3 would be negative 3, something to the negative 4, times the derivative of the inside, something, which would be cosine of x. So right now we have negative 12, combine those two, cosine of x times sine of x to the negative 4. But then I could get rid of my negative exponents and make that negative 12 cosine of x over sine to the 4th of x, or sine of x, the whole thing to the 4th. Hope you're following along. These really aren't that difficult. You just got to get used to the pattern behind how you do these. Now some of these can get a little bit longer. Say we have y equals the square root of the cosine of 3x. So this one you're going to actually see several different links to this chain rule. So you think of that as cosine 3x to the 1/2. Remember, as soon as you see square root, think to the 1/2. So what's y prime? So work your way from the outside in. You've got something to the 1/2. That derivative is 1/2 something to the negative 1/2. That's going to be cosine 3x. Now we work on the inside. What's the derivative of cosine of something? Well, that's negative sine of something. So that'd be negative sine 3x. Then times the derivative of the 3x. Notice that you took the derivative of every part of this problem up here. The 1/2, something to the 1/2, the cosine, and the 3x. Now it's just a matter of rewriting this. So I've got a 1/2, a negative, and a 3. They can all go to the front and become negative 3/2. Let's put our sign first, since it's not to a power. Sine 3x, cosine 3x to the negative 1/2. Now rewriting that without any fractional or negative exponents, we have negative 3/2. The sine 3x is going to stay in the top because it's got no negative exponents. But then cosine 3x to the negative 1/2 goes to the bottom as the square root of cosine 3x. Okay, and that would be your final answer. All right, let's look at just a couple more examples. How about this one? 1 minus secant 4x to the 3rd. So what's y prime? We're going to need some room for this one. The derivative of something to the 3rd is 3 something to the 2nd. now I'm going to take the derivative of the inside. The derivative of 1 is going to be 0. And the derivative of negative secant is negative secant something tangent something. Secant 4x says 4x with the secant and the tangent times the derivative of the 4x, which would be 4. Now again, just moving some stuff together, you got a 4, a negative, and a 3 that can come out to the front. So I would have negative 12, and then I'd only put stuff that's not to powers next. Secant 4x, tangent 4x, and then put my powers at the end. 1 minus secant 4x squared. And that's your final answer. There's nothing else you can do with that. All right, let's try one more example and we'll wrap up with that. So we've got y equals x cubed cotangent 5x. All right, so now this time we've got a multiplication problem. And x cubed times the cotangent of 5x, so we're going to have to do this as a uv problem. So let's let u be x cubed and let v be cotangent 5x. U prime would be 3x squared. V prime, the derivative of cotangent of something, is negative cosecant squared of something. So it'd be negative cosecant squared of 5x times the derivative of the something, so times 5. And now we do our Jesus fish. So we've got x cubed times negative cosecant squared 5x times 5 plus, then we do our other diagonal, 3x squared cotangent 5x. So let me go ahead and put our 5 and our negative and x cubed in the front. So I have negative 5x cubed cosecant squared 5x plus 3x squared cotangent 5x. Now I can look and see that I've got some factoring I might possibly be able to do. So we've got an x squared and an x cubed. So I could definitely take out an x squared. And because I hate my first leading term to be negative, let's take out a negative x squared. If I take out that, I'm going to have a positive 5x cosecant squared 5x. Then this will be minus, because we've got to multiply a negative times a negative to get this positive. And then it would be 3 cotangent 5x. And that should be our final answer. Like I said, we're going to do lots and lots of practice with chain rule. This really opens up the number of derivatives that we can do and all kinds of different things that can happen with those. So don't panic if you had some trouble with these examples. We'll do lots more practice in class. And you'll catch on. I promise it'll get better.